Bloodhouse Bio, unlocking the biopharma journey from genes to medicines.
So we have a very nice lineup. So with an intermission in between, and we will start with our first speaker, which is Professor Marcelo Fernandes-Lahore from Dublin University in Germany. People who are in downstream processing probably recognize his name because he is very famous in the area of expanded bed adsorption and among other things. And he will also be talking about certain aspects of expanded bed adsorption in this keynote presentation. So we are very happy that he is here and to show us the latest developments on expanded bed adsorption. So, can I ask you for
Yes, okay. Okay. Thank you very much. Thank you very much, Marcel. Again, thank you for the organizers or for the invitation. Thank you to the organizers for the invitation. And especially thank you very much for all of you coming today after lunch. It's normally a little bit heavy, right? So I am happy to have you in my presentation. So I would like to introduce and expand on the topic of expanded bed adsorption, so to say. And especially would like to show some progress that we have been doing in the last years, focusing on the applications of expanded bed adsorption as a technique to purify antibodies or recombinant proteins coming from mammalian cell cultures. So basically, very brief, I would like to introduce the technique for those who may not be familiar with that. Very briefly, I will then try to point out or put my finger into the problems that we still face with the technology, with the implementation of this technology, and then I will try to show how we are dealing with these problems and which strategies we are implementing to increase expanded bed adsorption performance in real practice, and of course it's always good to share some of our experimental systems, right, and experimental work. To introduce expanded bed adsorption, then let me show a small diagram here where you can see something that you already know, from bed chromatography. So you see there a couple of planares and something that represents a chromatographic material or an adsorbent in there, right? So in principle, this looks like a standard chromatography column. However, when we are talking about expanded bed adsorption, what we are going to do is to feed the column of the system from the bottom, actually, letting then the material inside the column to get fluidized. So de facto, we are creating a solid liquid fluidization system, right? The advantage of this is that then we can proceed to basically introducing a feedstock. This feedstock is actually a crude feedstock, so it contains cells in suspension or particles in suspension or biological particles in suspension. Those biological particles are going to be elutriated out of the system because there is a space between the particles or the adsorbent particles inside the system. They are going to be leaving, and then after washing, you could repack the column or just go for an elution in an expanded bed mode, perhaps using a little lower flow, right? So there is something very interesting to this way of operating the chromatography, so to say, and this is the fact that for the first time, chromatographers, we are now exposed to the idea or to the practice of introducing a crude feedstock directly to the column. Common sense in chromatography or common knowledge in chromatography would indicate that you need to very extensively clarify a feedstock before going to a chromatographic column, right? And this is what you do normally. So the direct consequence of this way of operation is that now we can at the same time remove solids, so there is a clarification effect, as you see here. There is also a concentration effect because we normally feed the system with several volumes of feedstock, and then we dilute in a few volumes of this feedstock, so there is a concentration, and there is also, of course, a more or less selective capture of a certain target molecule, depending on the affinity of the material itself, which, by the way, it can be operated in any chromatography mode, as you already know. So the setup of this technique is also relatively common. So you see some tubing, some pumps, in this case the static pumps, the column itself, and the chromatographic profile. This is an on-off chromatography, so you will be loading up to saturation, you will be washing, and you will be eluting one single peak, which is supposed to be pure due to the selectivity of the adsorbent. Okay, now in the last years, this technique was introduced in the, let's say, early 90s, and we already noticed at this time some degree of trouble with the technology, especially with the stability of the fluidized bed. And in recent years, we have seen the introduction of new materials, basically smaller and denser beads. All this in agreement with theory, right? This is still a chromatography, so it's still a diffusion limited process, right? So having a bead which is smaller diameter, less would imply that less diffusion is needed inside the binding sites, and then of course you will get a better performance. At the same time, if the particle is denser, you could flow the system with a relatively higher flow rates, and then productivity could also be increased or at least maintained. So smaller beads, higher density. Also, people notice problems at the level of the flow distribution, so also some attempts have been made in order to get some specific devices that would control the flow distribution at the bottom of the column. So this is basically the situation now. Now, there is a problem here, and the problem is that for expanded bed to operate properly, you should get not only fluidization, so the particles they are fluidized in there, right? You should also get a classification effect. So the classification effect basically implies that there is a restricted local mobility of these particles, the bigger ones at the bottom and the intermediate ones in the middle and the finest one at the top of the system. So with this relative immobility, so to say, of the particles, we are mimicking what we see in a packed bed column. And when we are mimicking what we see in a packed bed column, we are going into the concept of having several plates or several tanks or several stages of equilibrium. You know from distillation or chromatography theory, for example, that the larger the number of plates that you have in there, the better the performance. In the case of analytical chromatography, this is seen as better resolution or separation between peaks. In the case of an on-off technique, like expanded chromatography, you would see then sharper breakthrough curves, which is usually the way in which we look at the performance of these systems. Okay. So, for this fluidization classification to take place, you need no interaction between the feedstock particles and the adsorbent particles, which is not always the case. In many cases, you actually go into this situation, you see cells which are, let's say, adhering to the surface of the bead or even clamping on the surface of the bead, and the net effect of this cell adhesion or cell interaction is that the fluidization of the particles, the fluidization of the particles and the underlying hydrodynamics within the system becomes distorted, and you start looking at problems from this one, with, for example, shining and decrease or collapse beds, right? This is not good for capturing your product, and this can, at the systemic level, can be seen by, for example, utilizing residence time distribution analysis and breakthrough curve analysis, which are the tools that we will be using in any of these chromatographic systems. And okay, a well-behaved resistant distribution, preserved by hydrodynamics, correlates with very sharp breakthrough here, so we can use actually a lot of the variable capacity in the adsorbent without the system. On the other side, distorted aerodynamics, the relative here, you see how the tracer is coming very fast because there are channels, but also there is dead zones here, so part of the tracer is being retained or is spending more time, so to say, within the system. This also translates into much worse breakthrough curve, and if you calculate dynamic binding capacity as 10% of the breakthrough, so basically at this point here, more or less, you will see that here you are getting much less capacity than here, right? So the net consequence of this again is that you are spending a lot of money in buying these materials and you are using only half of the actual capacity, which would, of course, become a cost factor. Okay, microscopically, so these are the systemic resistance here, right? But if we look at microscopically, you will see under the light microscope pictures like this one, right? Control beads showing no addition with cells, for example. In this case, they are very nice, smooth surfaces, right? As soon as the interaction takes place, you see the cells binding and also clamps of these cells forming on top. So clearly, microscopically, we can actually see the phenomena happening, right? So the question here became how we can look into this situation, how we can look at this microscopic or even nanoscopic level to see what is going on there. And our solution to this question was to implement a thermodynamic approach or principles of colloidal chemistry, so to say. So we are looking now at free energies of interaction between surfaces or particles in our case, right? And we are taking some specific theoretical framework, so not the standard EBA technique that was basically minded in vacuum by physicists, but the extended ELBO approach, which is minded for particles taking contact or interacting in aqueous media, which is, of course, the bioprocessing situation, right? So in this extended ELBO approach, we are looking at three different components. These different components are related to Lifshitz van der Waals forces, acid-base forces, so electron donor and septic ability of the interacting balance, and of course net charge. Then the second point here is okay, how we can assess, how we can measure, how we can determine these components, or how we can get an idea of the relative contribution of these components. And of course, we are experimentalists, so we look basically for a experimental approach to that. And luckily, it is possible to access these two energies, or these two energy components, LW and AB, via measurement of contact angles, and the electrical component via measurements of particle charge or zeta potential determinations. Right? So we went into doing this kind of determinations. I will not explain every single detail here, but just to let you know or to understand that these techniques for the kind of measurement, for example, are used by physicists on very smooth surfaces of materials, right? In this case, measuring contact angles on cells is much more difficult. There is a specific time window under which you can really do an accurate measurement. So it was a lot of work for the development of the right techniques and the right portfolio here. And for cells, you can do it, okay? You can basically deposit the cells on ultrafiltration membrane, as you see here, and you can get a smooth surface, taking care of not excessive rotation of the layer. But what's happening with the particle beads, right? If you're having beads, chromatography beads, which are 200 micrometers or so, this is not possible anymore. The rule of thumb is that particles, they should be lower than 10 micrometers to be forming a smooth enough surface to be used for contact angle determination. So we started breaking down the beads and depositing fragments And then, of course, it was a nice colleague of mine who started criticizing my paper, I could say, saying, okay, but the bead, if you are breaking the bead inside, is not the same as the outside, or whatever. So he has got a point, I would say. So we went into the development of this other technique, the capillary method, where you actually pack your beads in a small tube, and then you can do the determination of contact angles, which are calculated from the penetration, the capillary penetration of different diagnostic liquids into this small packed bead that you have there, that resembles very well the situation under chromatography conditions. So here, to make it very simple, what you do is you use 3 diagnostic liquids, for example, water, formaldehyde, and alpha-1 to mention 3, and you are able to get from these contractive measurements surface tension components, and with these surface tension components, you are able to calculate the delta G's that I showed before, right? Okay. In order to assess charge, the normal way to go is to use a synthesizer or a microelectrophoretic device, because the charge of the particle is correlated with the electrophoretic mobility, in this case inside this commercial cell, right? So from electrophoretic mobility experiments, you can determine the charge of the particle. Again, for the cells, this is a piece of cake, but when we go into the chromatographic particles, they may be sedimenting in this kind of chamber. If we break the particles, again, my colleague would come and say, okay, we're breaking the particles. So we went into a different approach, which is a streaming potential approach. Here, you basically pack the beads in a small chamber, and then by flowing a liquid with a certain pressure through this chamber, you are disturbing the ionic atmosphere around the particles and generating a differential potential, which is actually measured, and from there you can again infer the zeta potential or charge of the particle under certain conditions. So we started this method, and then the next question is how you actually use the information that you get from contact angles and from zeta potentials. Well, you basically use a set of equations to make it very simple. These equations are going to calculate potential energy of interaction here. This is important because the delta G's that I showed before, the equation for the calculation of delta G's that I showed before, are energies calculated between basically 2 planar infinite surfaces per unit area or so. So, and at a certain distance, which is a couple of amps. So, we have to bring this to the real situation, and the real situation here is a small particle in the cell and a big particle in the adsorbent.
So we can have an additional simplification here and say, okay, since the radius of the cell in the case of the radius of the adsorbent particle is pretty small, 20 times difference, so we can consider the big particle to be a plane, or is a planar surface, and then the only radius that enters the calculation is the radius of the cell. So this simplifies a lot, and if you look here, basically you can see that the energy
component is basically the zeta potentials of both the cell and the adsorbent. The LW component is basically fed with the delta GW, which is embedded in this gamma constant. As a matter, is another way to look at the delta GLW. And for the AB component, we will see here also a delta GAB that is calculated from contact angle measurement. So, with 2 relatively simple experimental methods, contact angle determination and zeta potential determination, or streaming potential determination, you fit these equations and you get something like this, where all the components are, or the energy due in units of kT in this case, as a function of distance, is going to give us an idea, or a more quantitative picture, on the energy that 2 particles would feel, so to say, when they approach or when they divert, right? Or when they lose. So, what we take out of this picture is basically the depth of the total curve here, or the total energy curve, which is the black one, right? When this is negative, this indicates a thermodynamic tendency or preference to actually for these two particles to actually interact, so we could predict addition of cells on the material when the peak is not present here or is even going in this range, right? This will be repulsion and there is no danger of any cell addition. Okay, so we wanted to corroborate that these calculations are really useful, and for that we started working at the lab scale using a couple of simple techniques. In these techniques, this is basically a scaled down standard bed absorption where you inject courses of cells. The more cells you get at the exit of the column, the less interaction there it is, right? So this is called the cell transmission index. And on this side, there are small wells in the microwell plate, right? Where you have the contact particles and the cells, and you basically measure the supernatant after some contact time, and you see how much cells they remain in the supernatant. The more cells that remain, the more contact, of course, the more, the less interaction you have. This we call the cell partition index, and to a certain extent, these two techniques are good. So, a correlation between the energies of interaction on this side here and the cell transmission index of the cell partition index on this side, it actually provides a nice correlation, in this case also for mammalian cells. There is, I'm showing relatively simple graphs here, but we have many publications indicating that this is actually the case when we work with different types of biomasses, and especially yeast and bacteria. So this corroborates the general applicability of the approach. Okay, another question, a little bit more basic, was are these energies really meaningful? How we can assess how we can access these forces in a different way. A different way would be to determine direct contact forces, right? And this we can do with atomic force microscopy, and this we did. So we basically glue the chromatographic beam on the AFM cantilever, here on the top, and we expose this modified cantilever with the cells deposited on the ground surface, and we got, this is just one example, but we got trends like these ones. This is, for example, a negatively charged particle bead or chromatography in contact with cells which are normally negatively charged, in this case, these cells. So you see there is a repulsion here, and the more salt you add to the system, so go in this direction now, right? This repulsion decreases because you are masking the charge. And the calculations mimic exactly the same trend. There is a separation distance measured by the AFM, and by the calculations is 1 order of magnitude different, and we are exploring why this is happening. We don't have the answer yet. We will see in the future. Well, okay, so now that we have these techniques and that we have this theory, how we can really apply this to a real solution. So a real solution here would be to, for example, modify the mobile phase in order to increase the performance of the certain process. So we went into actually doing that. We ran calculations and we build up three-dimensional plots, and these ones that we see here. So here at the same time, we can see the energies that are calculated as a function of three parameters, which are critical for operation, which are total ionic strength of the buffer or feedstock, pH of the same, and the composition of salts that you have in this buffer, in this culture media, or whatever feedstock you want to apply. So we can actually, in the calculations, remove or add salts in order to find optimum spaces for the process. And we went into testing this in real practice with DSM Biologicals in the Netherlands. And this is what we did. This is the capture of the protein A capture of the monomer antibody. This is the current protocol here. We suggested three lines of kind of improvement or potential improvement, and modifying the pH or adding salts or changing the ionic strength in these cases, as you see here. And the result of that is that we actually observe, for example, that modification of pH helps you to trap more products, so the The red line is the current protocol, and the blue and the black ones here are basically the improved protocol in comparison with cell-free feedstock. So we basically shift from the red situation to the blue situation here. There is already an improvement at the level of the capture of the product. And then we ran the whole cycle, so we went through the application of the sample, of the feedstock, 2 washes. There are 2 washes steps here, and finally there is of course the dilution of the product. And when we look into the final results, analyzing the whole purification run, you see here that when this is the current method that they have had at the time, with, of course, with recovery and purity and low level of aggregates, our suggestions are able to improve recovery, and they are also fulfilling very well another prerequisites like purity and aggregates. Perhaps this sole exception here, which is not critical as well, but nevertheless. And this clearly demonstrates that by changing mobile phase composition, it is possible to improve a very well-tried and well-tested application, like the purification of molecular antibodies on protein A, right? So the margin that you have to improve this kind of process is really small, and nevertheless, the technique allows us to look into this situation. Okay, I am going to show quickly now a second possibility, which is instead of modifying the mobile phase, what's happening if we are shielding the bead or protecting the bead against any interference, right? So we are based on previous work by us, but I am going to show you just here something that we did, which is we screened for polymers for actually protecting protein A or mixed mode beads against cell adhesion. And this screening resulted in the diagram like this one that you see here, and a few polymer candidates are on top of the diagram. So this is low energy and high adhesion index, so low adhesion of cells. So we went into protecting our cells with this polymer. And when we look at the read-throughs, right, the unprotected bead versus the protected bead has helped us to actually win 50% of capacity during the real processing conditions. So there are 2 basic ways to use these tools, either by looking into mobile phase composition or by guiding the material. Thank you very much.
Thank you, Professor, for this very nice presentation. It's technique. There's room for questions. One here.
Thank you, Marcelo, for a very nice presentation and good work. I'm actually intrigued with this work. So when you modify the surface, when you go to a surface with the polymer, you see more change in accessibility towards the beads. So how can we increase? It's not just a little increase, it's 50% increase of the capacity.
Yes, well, this is the preliminary data. As you see, it's a very raw kind of picture that I'm showing here. In principle, I am not sure that by so to say, shielding the bead with the polymer, we would necessarily block any kind of pores, right? Because if there is a physisorption of the polymer on the bead, for example, this polymer, if the molecular weight is not so big, would eventually enter also the pores and basically be on the surface of every pore, right? Or what it would.
Thank you for watching. Like, share and subscribe.